Development Council. He received his MSc and PhD degree from the same university. During his tenure, he had several additional posts, being head of chemistry department, coordinator in university industry, in linkage program, dean in the faculty of sciences, professor in charge examinations in the office of controller of exam. His research area includes chemical sensors, colloids and interfaces, environmental chemistry and electrochemical methods of analysis. In the field of surfactant chemistry, he is currently focused on exploring the interactions of surfactants, ionic liquid with drugs so as to utilize their potential as drug carriers. He has been research supervisor of 23 PhD and 61 MSc students and is still guiding about 7 PhD students. He is a reviewer of various research schemes submitted to UGC, CSIR, DST and Ministry of Forest and Environment. He has been a visiting scientist to several foreign countries including Italy, Japan, Spain, South Korea, Taiwan, and also delivered numerous invited talks and tutorials in various national and international conferences. He has the honor of being a chairperson for many technical sessions at several workshops and conferences. His organizational skills have been well manifested in the form of convener, organizing, secretary and chairman in many conferences, seminars and workshops. I am glad to inform that Indian Chemical Society bestowed him with C.K. Bose Memorial Award 2009 at Annual Convention of Chemists Raipur in December 2010. Recently awarded CRSI Bronze Medal by Chemical Research Society of India at the 16th CRSI National Symposium in Chemistry held at IIT Bombay during Feb 7-9 2014. Elected Fellow in the year 2015 of the National Academy of Sciences, India. Thank you.
Thank you, madam, and very good afternoon to all of you. And also, I would like to thank Dr. Rajeev, coordinator of this program, and of course my friend Dr. R K Sharma and Dr. S K Mehta, and we are very close friends. So if Dr. Sharma is there, we too are supposed to be there now. So in this way we coordinate each other, and in fact one it was delayed by 1 day because of me only. I take responsibility of that. And you have listened to very basics and the talk, but I was also not knowing about the thing that the audience which are likely to be from BSc, I thought that there must be some MSc students. So I thought that I should give a talk about the chemical sensors which we have prepared in our laboratory for the last so many years. I mean, for the last 13 or 15 years. So anyhow, I will take up preliminary introduction of these sensors, and I will, since there are my colleagues from the other, from the chemistry department and other department, they can listen to my talk and they can start their own research here in college, because the research, the sensor which they can make, that can be utilized for the measurement of some cation or anion in the different type of the matrices. And these matrices may be some environment samples, maybe water samples, soil samples, blood samples, urine samples, or like that. So with this background, so
क्लिक कर दो, खोला ही। Yes, sir.
I don't find this. Because the topic is about the electrochemical sensors for cation and anion recognition. And you know the cations and anions, especially the heavy metals, metal ions, nitrate or chloride, and these type of the anions, they are also cause some hazards, and they are detrimental to the human being. Heavy metals are also like that; they are toxic. So we prepared that how we can online monitoring some of these cations and anions. So the okay. So can I have this pointer?
On the right hand side.
Anyhow, we have been talking, we have been doing search in our laboratory on different fields, and so we have been doing some work on sensors, and especially sensors based on some voltammetric sensors, that is electrochemical sensors, where electrodes are involved. And in voltammetric sensors, we do some cyclic voltammetry, which may be in your syllabus, or the differential pulse voltammetry, where there is nothing that we change the current, and there is we change the potential, and with the change in potential across the electrode system, there is a change of current take place, and that current is a function of the concentration of the analytes. That's the basic backbone of our measurement in voltammetric sensors. In the potentiometric sensors, what is the measurement is that there is a change of the concentration. With change in the concentration, there is a EMF change take place across the electrode system. So we get the straight line like that, and this is which measure the concentration range of this. So, and in addition to that, we are also doing some of the search about the colloids and interfaces. In colloids and interfaces, what we are looking at the surfactants and additive mixture concentration. What happens to when we add additives? What happens to the properties of the surface active agents? And these additives can be any organic molecule, maybe an triglycopolymer, maybe an drug like that, and and then ionic liquids are also the surface active agents, and they interact with the drugs. So this is what we have been doing in our laboratories. My talk will be concentrating to the electrochemical sensors, that is especially the potentiometric sensors and the voltammetric sensors. Now what is the chemical sensor basically is? So to know that, the chemical sensor basically is a small device that can be used for the direct measurement of the analyte in any of the sample metrics, and is capable of responding continuously and reversibly, and does not perturb the sample at all, and produce accurate, reproducible, and fast and selective determination of the various ionic species. That is, it is not being interfered by the other interfering ions, and they are adaptable to a small volume. That if you have a small volume of the matrix, you can measure the concentration of the cation or an ion in that sample. So with this, these are the different features of these chemical sensories, and this, because of these methods, they can be utilized for online monitoring of different cations or anions in different samples, like in medicinal, environmental, or agriculture, or industrial fields. Now, what is basically the theme behind these sensories? The first thing is the selectivity of sensories. That whatever you are making that is the sense, that sensing the particular type of the cation or anion is not being interfered by the other ion. That is important. And the other thing is how to sense it. If it is selected to particular type of the species, that how to sense it. So with this, you need some transductions. So method of transductions are electrochemical methods and maybe spectroscopic methods. The electrochemical methods can be potentiometer. Electrochemical method can be voltammetric. What does mean this? That if you have a potentiometric sensor that measure the potential, and that potential is proportional to the concentration of the species. And in voltammetric sensor, the current is as a function of the concentration is. In all these type of the electrolytic techniques, three components are involved basically. One is maybe current, maybe potential, maybe the concentration. If the potential is proportional to the concentration, or is proportional or varies with the concentration, we call it as potentiometry. If there is a change of current with the concentration, we call it as a voltammetry. So the other spectroscopic techniques can be UV visible. That, for example, in colorimetric sensor, what you are measuring is that you change the concentration of the species, there is a change of color density changes. And if the change of color density takes place, you measure the density and you plot the color density, intensity of that absorbance, whatever it may be, versus the concentration, you get a straight line. So this is how you can use the different techniques. For example, in a fluorescence spectra also, you measure the fluorescence intensity, and that fluorescence intensity is proportional to the concentration of the species. So different type of so I will touch upon only these type of the sensors, potentiometric and voltammetric sensors. Now what is a potentiometric sensor is? If you look at this, you should think of the pH meter firstly. What is a pH meter? pH meter is a potentiometer. You know, in pH meter, you always have the two knobs. One where you measure the pH, and there you measure the millivolts. So in a pH meter, you have a glass membrane, which is an iron membrane, glass membrane, which is your working electrode, which is your indicator electrode, and it is very much selective towards the H positive ion. So that glass electrode is an ion selective electrode for the H positive ion. That is why H positive ion, you know that pH is equal to negative log of hydrogen ion concentration. That means in pH meter is. So, similar basis, you can make an ion selective electrode for other ions also. And if you see that, what is the basic behind this? What is the basic principle of a potentiometric sensor is? That you have a ion selective electrode, which is a membrane, this membrane, and then you have an internal solution over here, and in this internal solution you have a internal reference electrode. This is an internal reference electrode, and this one is an external reference electrode, and this external reference electrode can be a saturated calomel electrode, can be an silver chloride electrode. Now the question arises, can we make these electrodes in the laboratory? Yes, we can make the laboratory. In fact, we should have a practical which should be introduced in the BSc level, that to prepare an calomel electrode, to prepare an ion selective electrode, to prepare an reference electrode, silver chloride reference electrode. That's very easy to prepare. For example, if I am interested in making the silver chloride electrode, that is easily available. Then you can go to the jewelry shop and can buy with 10 rupees a silver wire. A small silver wire you can buy, and that silver wire you just put in a beaker which contains about 0.1 molar HCl, and along with that you have a platinum wire. You buy an ablative cell, maybe a cell of 1.5 millivolt of 10 rupees again, and then you connect with the copper wire. These two electrolysis will take place, and you will see that on the silver wire on the surface of silver wire, that will get blackened or whitish and black, and that is just a layer of silver chloride that will form. You take away and wash it with water, and that silver chloride reference electrode is ready to use. So this, with few rupees, you can make a silver chloride electrode, and that silver chloride electrode you can put there, here, in here, and then you can make a membrane. How to make a membrane is that I will come to later on. Now, this also have this is being placed in the internal solution, and the concentration of the internal solution is kept constant. For example, if this membrane is a glass membrane, and this is for pH meter, this solution should be the ions which you are measuring. In pH meter, what you measure? The H positive ion concentration. So that means I must have an internal solution whose concentration known to me. And that, in fact, in pH meter, in glass electrode, in the bulb, you see a 0.1 molar HCl solution is there. So 0.1 molar HCl is there, and and then it is being connected with an external solution, external reference electrode, maybe a saturated calomel electrode, and this can also be easily prepared by making a calomel. Calomel is nothing else but it is a mixture of mercurous chloride, mercury, and potassium chloride. You just have this in the pestle mortar. You make it a white paste, and put this white paste in a test tube, and you, with a platinum wire, ask the glass blower to make a platinum wire, and with mercury on it, and copper wire that will also act as a saturated calomel electrode. Connected with that, and then when it is being connected, you have a potentiometer over here, and this potential measuring device is a potentiometer which measures the potential across the system is. Now this, so what you need is, you need an ion selective electrode, which is your membrane here. You need a reference electrode, that is this one, and you need a potential measuring device, that is your potentiometer over here. This is a simple assembly. Now the question arises, how this potential develops across this membrane is. Now, if you look at this, to make an ion selective electrode, you can think of how to make an ion selective electrode. The ion selective electrode are ion selective membrane. I can make ion selective membrane very easily. How? That is, I can have any ionophore. Ionophore is a species which may be an inorganic compound, maybe an organic compound, maybe a neutral species. So whatever, or maybe any other matrix which is capable of selecting a particular type of the cation is. For example, when this type of research started to have an ion membrane, in 1964, the first membrane which was prepared by Kramer, and that Kramer in 1964, he took blenomycin, which is an antibiotic. That blenomycin antibiotic, he incorporated the blenomycin in the PVC membrane and make a membrane, and that become selective to particular type of the ion, and that ion which it extracted is the potassium ion. That was selected to potassium ion. And another antibiotic, that was nonacin. Nonacin was another antibiotic, and that antibiotic was selected towards the sodium ion. So those membranes were selected to particular type of the cation or anion is. So there are different compounds. For example, you can think of some compounds, organic compounds, like crown ethers. You have studied the crown ethers, and you know the crown ether, they have the capacity, they can extract the lithium ion, they can extract potassium ion, they can extract sodium ion, they can selectively bind with these ions, alkali metal ions. So you can use that crown ether, you can use the calexin, you can use other organic materials, you can use even inorganic materials, and those inorganic materials you can incorporate it in the PVC membrane. How to make that? That's very easy to prepare. What you need is, you need just 5 or 6 milligram of an organic compound or inorganic compound. You just take a small beaker. That beaker is just of 10 ml, and in that 10 ml beaker, you just take 5 milligram of the ionophore, the organic compound or inorganic compound, and you mix it with some softener, the plasticizer. Plasticizer is a softener, and that plasticizer can be it makes the membrane to be a soft one, and that softener can be any compound. You can take diethyl ether, it can be an ester, diethyl phthalate, can be another ester. So ester and ethers, they make the membrane to be softer. That is why the plasticizer is also referred as about let's say 35% of plasticizer you take, 5% of the ionophore you take, and rest you 60% you take polyvinyl chloride. Polyvinyl chloride are sometimes some additives 2% or 3% of ionic additives like surface active agents are being added to have a donor membrane. So you mix it with the glass rod with the 5 ml of tetrahydrofuran. Just mix it in the small beaker, and when you mix the whole components, all the 4 components, then you take a petri dish of 10 centimeter diameter. So just take a small petri dish and pour that solution into the petri dish and keep that petri dish overnight in the laboratory, in the room. You will see that in the morning there will be evaporation of the tetrahydrofuran, and on the surface of the petri dish you will get a clear, very clear, transparent membrane. That membrane which you will get, you ask your glass blower that you can take a small test tube, and that small test tube you can cut the close end also, and then you put that with the help of the glue, you keep that membrane, that glass tube on the membrane, and with the help of glue you can mount that membrane. So your membrane is ready. This is how you can do. See here, you can have mix these together in a beaker, and then you pour it in the beaker, and this is the membrane which is transparent, and you can put this transparent membrane over here, put your silver chloride electrode over here, and this is ready to use for the measurement of your tensiometrics measurements. Now this is a very easy to prepare and very easy to use this, and you can see here that this is of course the properties of an ionophore. Ionophore is a main component of ion selective membrane, which is a neutral or charged compound, are able to form the complex ion reversibly and to transfer them through the organic membrane. The essential feature is it should be capable of selective formation, complex formation with the primary ion, should not be responsive to the other cation or an ion. Its ionophore must be retained in the membrane phase. It should also retain in the complex with the membrane phase, should not allow the complex diffuse freely in the direction of the potential gradient which you are applying. The kinetic of the ion transfer should be very fast, and the stability constant of the metal and the ligand, that should be not very high. It should be moderate nature, neither high nor. These are the properties of an ionophore, which the backbone of our ion selective membrane is. The plasticizer influences the dielectric constant, and this plasticizer dielectric constant, and these plasticizers, they are added to the membrane in order to have a good chemical and physical and electrical properties. And the third one is the ionic additive. Ionic additives can be your this type of the compound, sodium tetraphenyl borate, or these are the hydrophobic membrane to make them hydrophobic, and these are being used generally surface active agents. And polymer matrix, which polymer matrix is the PVC is an inert matrix, polyvinyl chloride, and this provides the mechanical strength to the membrane. Other polymer can also be used. For example, I can use the polystyrene, I can use the polysilicon, I can use the polyimide, and polyimide can be used for the membrane preparation. And these are the common composition of the making a membrane. PVC 33%, plastic 60%, ionophore additive, and if you take this proportion and mix them in tetrahydrofuran, and you will see that there is clear membrane will be formed out of this, and this is ready to use. Once you have this membrane, the membrane which you are putting here here, this membrane is being shown over here, and if you see here the membrane which is being shown, that it looks like this. This is membrane, right? You have an internal solution here. The internal solution, the metal ion, and this L is your ionophore. It forms a complexation, and this complexation is being formed over here. So because of these two reactions, that this is from the internal solution coming to over here, and this is happening, the potential will be developed, and this potential which is being developed is the membrane potential and the boundary potential is. And boundary potential over here, and the other potential which is developed because of this reaction. Remember that in all these pH meter, in all these type of the ion selective membrane, there is no oxidation and reduction in it. If you are using any ion selective membrane, if you are using any glass electrode, potential, the oxidation reduction process is not taking place. The potential which is being developed is purely on the basis of the forces, that the forces which are taking place because of this, these are the driving forces. So this potential which is developed here in this surface, here is due to this reaction. This develops over in the surface which is pointed to the external analyte, that is due to this. So this reaction, so these driving forces are responsible for this. So these two potentials are being developed. So what you are measuring actually is the difference between the two potentials, and the difference between the two potential is known as the diffusion potential, diffusion migration potential, or sometimes we call it as boundary potential. So boundary potential which we are measuring is, and that boundary potential, when you are changing the concentration over the analyte over here, this ED also changes. So ED versus the concentration of the analyte, that will give you a straight line if there is selective to particular type of the ion. For example, in glass electrode, in the glass electrode pH meter, you get a straight line. Why you are getting a straight line? Because that glass is selective toward X positive ion only. It's not selective. It is not being influenced by the other ions like sodium ion or potassium ion. Now, this is a response curve. The response curve is generally given by the EMF measurement, and this EMF versus the concentration of the analyte, you get a straight line over here. And you know the straight line which provides you the Nernstian slope. This is the slope which is a Nernstian slope, and this Nernstian slope is based on the Nernstian equation, and that is 0.059 over n in the Nernst equation. 0.059. So 0.059 over n. If it is monovalent, n is 1. N is 1, then it means it is a 59 millivolts. If it is 2, divide 59 by 2. So if you are getting this the slope, Nernstian slope, then your ion selective membrane is good. If you are not getting the slope according to Nernstian slope, then your ion selective electrode is not good. So we have to check once you have got the ion selective membrane, and that ion selective membrane, ion sensor, that sense particular type of the ion, we have to optimize the conditions. We have to optimize it by looking at the slope of that slope. We should, if I am using, for example, blenomycin. If I am using blenomycin as an antibiotic as for the potassium ion sensing, it means blenomycin that provide that is selective towards the potassium ion. If in a sample I have a potassium ion also, I have a sodium ion also, I have a lithium ion also, then what will happen? That ion sensor will be not selective to particular type of the ion. It will be influenced by the other ion also. Then we have to look at the selectivity coefficient. Selectivity coefficient is a very important parameter to measure to know that the sensor which you have made is selective to particular type of the ion or not. So that what is then the selectivity coefficient of ion selective membrane is? The selectivity coefficient is selectivity is the most important characteristic of any sensor, which define the nature of the device and the extent to which it may be employed in the determination of the particular ion in the presence of the other interfering ion. And the degree of selectivity of the primary ion, for example, I have made a sensor for the A ion, and B ion is an interfering ion, so I must have a K potential A and B. So I must calculate the K potential A, B, where A is a primary ion for which you have made the membrane, and B is your interfering ion. And log value of this, if the log values of K potential AB that comes to be negative, it means B is not interfering. If the log K potential AB value comes to be positive, it means there is the interference of that B ion is. So now the question is how to calculate the log K potential or K potential AB value. There are different methods. The methods are separate solution method, mixed solution method, matched potential method. So what these methods are, for example, in separate solution method, what we do is, we take a primary ion A and we take the interfering ion B also, and we measure with the help of the ion selective membrane which you have prepared, you measure the potential. If the potential measuring by EA is giving you this one and EB this one, but then the solution containing B with no A ion, that is separate, A and B are separate, and this method is not good. Good in the sense that in real sample you always have the interfering ion. So it means this type of the method is not useful. So what we do is, we generally try it with the mixed solution method. Now in mixed solution method is, you mix A and B together. Interfering ion also with the primary ion. So in mixed solution method, that you measure the potential in the presence of A in the presence of B. So what we do is, we do in two different ways. One way is, we have a fixed interface method, and the other is two solution method. What we do in fixed interface method? In fixed interface method, what we do is, we have a different concentration of A ion. Let's say 10 raised to minus 1 to 10 raised to minus 10 molar of the 10 beakers I have of different concentrations of the primary ion. And in every beaker, I put the fixed amount of B ion. I put the fixed amount of the B ion in every beaker. And then I measure the potential of each there. And when you measure the potential of each, you are keeping the fixed concentration of the B, but you are varying the concentration of A. In that case, you will get this type of the curve. And at this point G, so where these two the values are meeting at this G, but at this point G, EA becomes equal to EB, and then you calculate the K potential AB is equal to activity of A, activity of the B concentration, and they are raised to power their charges on the A, charges on the B. So fixed interval method is widely used, generally used for the measurement of this. In two solution method, that involves the measurement of the potential of a pure solution of the primary ion EA, and mixed solution containing both the primary and the secondary ion, interfering ion, that is EAB. And these are the equations which have been used to calculate the K potential AB. So there is another method, and the mass potential method. In the according to mass potential method, the selected coefficient is being calculated is activity ratio of the primary and interfering ion, and these are the equations which are being used to calculate the K potential AB. So K potential AB is very important parameter to determine that. With this type of the background, and of course there is another type of the sensor which I will be taking up a little bit, that is the voltammetric sensor. In voltammetric sensor, what you need is, you need three type of the electrode system. One is the working electrode. You need a working electrode, maybe a mercury, platinum or gold or glassy carbon electrode or silver electrode, and the other is the potentiometer, the reference electrode, maybe saturated carbon electrode or silver chloride. Another is the auxiliary electrode, maybe a platinum wire to compensate IR drop, and sporting electrolyte. Of course, some of the ammonium salts or alkali metal salts are being taken, they percolate, or the tributyl ammonium percolate salts are being taken in to reduce the ohmic drop and migration potential. This is the what you have is the that you have a reference electrode, the counter electrode, and then the working electrode, maybe a dropping mercury electrode, or maybe a platinum wire, or maybe platinum or glassy carbon electrode. So this tip is the electrode. Now you also bubble nitrogen through this, and through this solution you vary the potential, and when you vary the potential, there is a change of the current take place. And if you look at this, this is what is the potentiometer looks like, and you get the current versus the potential. There is a peak current take place on the anodic reaction take place, and then when you reverse the switching potential, there is the same species which is being oxidized is being reduced. So this is a cathodic potential. So you have a anodic potential, you have a cathodic potential, and this is how it looks like that you get to the cyclic voltammogram or the differential pulse voltammeter. With this background, our focus was generally to measure the silver ion selective electrode, to make cesium selective electrode, mercury, chloride, nitrate, iron sulfate sensors, and the iron 2, iron 3, copper 2, zinc 2, amino alcohol, urinary sensor, ion pair recognitions, surfactant selective electrode. So I will take up little bit, because we have done a lot of work on this. I will just take up little of these, little bit of the results which we have published for the last 10 years or 15 years. So this is we started in 2000, around 2001 or like that, and we took the first sensor which we made with the help of the Claxrin molecule. Now this Claxrin molecule having different spacers. This spacer is, and this spacer is, these are the 10 spacers. These are the 10 spacers. So 5, 6, 7, 10 spacers, and these Claxrin molecules, when we did some preliminary experiments, we find that this is very well selective to extract the silver ions quickly. So we made, what we did is, we incorporated this Claxrin molecule in PVC membrane. I have told you the method how to make it. Claxrin, PVC and plasticizer all together in a tetrahedron. Make a membrane and mount the membrane on the surface of the tube, and you can have your ion selective membrane. And that ion selective electrode which you can make is, that Claxrin molecule which you can make is, that is selective towards the silver ion. Now you know that silver, when we published this type of the work, earlier whatever the work was available, silver was being interfered by the mercury ion. You know that silver and mercury have the same radii. They have the same size. So therefore, they interfere with the measurement of each other. Silver, when you make silver, measurement silver in the presence of mercury, mercury interferes. When you do vice versa, the silver will interfere in the measurement of mercury. So this was the first report where we indicated that the silver selective electrode is not being interfered by the other mercury ion especially. So what we did is, we just incorporated this, and this was the composition. We have the 10 electrodes which we prepared by using the 10 compounds, different 10 compounds. PVC was so much of the percentage, and this was the dichrysabagate, and then this was the ionophore, that is the Claxrin molecule, that was so much percentage or maybe milligram, and the linear range which we measured is 10⁻⁵ to 10⁻⁵ molar. So if we have let's say silver ion concentration 10⁻⁵ or 10⁻⁶. So this 10⁻⁶ molar, this was the traction limit which we were obtained, and slope was also good. So this is how all these 10 electrodes using the 10 compounds, they were giving the good results for the silver ion measurement. So this is what it looks like, and this is how it looks like, that you have a 10 compounds, 10 membranes, and they give you these and here to here is the concentration range. After that, this becomes constant. After this concentration 10⁻⁶ molar, the potential does not change at all in all these cases, constant. So we are interested only in this linear range, in this straight line, and this was the detection limit which we obtained for this. And if you look at this one, we have looked at the effect of pH, and you can see that the effect of pH at all these 10, the pH range is approximately 1 to 7. There is no change of the potential take place with the pH. But after this, after 7 pH, there is a drift from the measurement. The potential changes. Why potential changes is because the silver hydroxide is being formed. So it is not only responding to silver, but it is a silver get hydrolyzed, and it get formed the silver hydroxide. So whatever the measurement you want to carry out for the silver measurement, that is with in this pH range. So this is the effect of pH. This is the effect of the plasticizer. Dichrysabagate has been found to be best one, and this is the selectivity coefficient. I have told you log K values. Log K value which we have calculated. This is the silver, and B is this one. B is potassium, sodium. All these are B interfering ion. When we calculate for all these 10,
we were interested in mercury, for example. All these values are negative, and we were interested in mercury, and look at this mercury. Mercury is giving you the log K value also negative. It means there is no interference of the mercury ion in the measurement of the silver ion. So this is we also did the potentiometric titration. What we did is we have the ion selective electrode. We place that ion selective electrode in a beaker, and in a beaker we have a silver ions, and from the birute we added the sodium chloride. When we added sodium chloride, the chloride ions, they react with the silver ions and form silver chloride precipitation take place. And when silver ions are depleted, there is a change of potential take place. And this is how the change sigmoid plot is being obtained. This is the potentiometric titration, which we did it. In potentiometric titration, this is when you add the sodium chloride. So this is, and from here you can calculate the end point, whatever the volume of silver chloride ion is taken. From that you can determine the concentration of the silver ion by using the simple equation N1 P1 is equal to V2. You can determine the concentration of the silver ion or the chloride ion. Determination can be carried out. So this is another, we prepared another by using this type of the ionophore, calyx for crony ester. And if you see that, this is also extracting the cesium ion. So what we did is, we prepared the membrane of this compound, calyx 4 crony ester, and used it for sodium and potassium and cesium. So we find that there is no good result with sodium and potassium, but cesium, if you see this cesium, gives a very good response toward this. So multi-electron, multi-metal system we perform, and this we find that cesium selective. And since this is linear range, this is slope, because cesium is also cesium positive, so this is the detection limit. So we also made the selectivity data, and selective data, if you look at the selective data, there is no interference of any of these diverse ions. So it means this is selective to, all these values are negative, indicating no. So this is another sensor which we made for the mercury ion, and that mercury ion that was based on the molecule, that is your different compound we have used. We have used thiosemicarbazone, and thiosemicarbazone, where thiosemicarbazone is your, these are the different species over here. So we have added here, and in these derivative, thiosemicarbazone derivative, and also some oxodiazepine phosphine derivatives, we find that they are selective towards mercury ion. We incorporated it, and we find that this is for example, thiosemicarbazone. We made the membrane. When we made the membrane, no other metal ion is giving any response. But if you look at this mercury gives a very good response. And this mercury, and if you see that mercury, the linear range is this one, detection limit is 10 to minus 6, and the slope is, because mercury is Hg2 positive, therefore it is 29 millivolts, inertial slope. And if you see this one, and this is how the selective data of the mercury is. But here, if you see that, the silver ion, if you look at the silver ions here somewhere, they are interfering in our measurements here. So this is the positive value. So it means this sensor cannot work in the presence of silver ion, but we can determine the mercury in the presence of other ions. So this is the potentiometric titration of the mercury ion with EDTA. When we did titration with the EDTA, they formed the mercury complexation, and this provides you the sigmoid graph again, and you can determine this. This was the chloride ion selective sensor. We did experiment in collaboration with in Japanese Osaka City University. I was in Osaka, and there I gave a talk, and then he asked me, the Professor Skube, that why don't we make the collaboration. So we did the collaborative work, and in that collaborative work, we made the sensor that is based on lanthanide tris beta diketone complexes. So that is based on this M is praseodymium, europium, terbium, dysprosium, and this will be europium. The europium, and the other one is also europium. So 7 complexes we took, And you know that these are the lanthanides, and lanthanides can extend that there are 6 coordination number. The coordination number is the 3 means divalent, the bivalent, what do you call as the bidentate ligands, and the coordination number is 6. So it can extend this coordination number beyond, even you can have 8, 9, 10, even 12 coordination number. So we did some experiment, and when we did some experiment and we did the ESIMS, we find that this is selective toward the chloride ion. When we added chloride ion, it forms a negative MS signal due to the highly coordinated complexes being formed. Now we made the membrane, and when we made the membrane different pH, and we find that these all 7 compounds which we have made the membrane, some having pH, some can work in this pH range, some are working in a very small pH range, that after below 3 pH, the all complexes are expected to decompose, and after that the hydrolysis starts, or you can say the membrane become sensitive towards the OH ion rather than the chloride ion. Now then we added different cations. When we added different cations, those cations are not interfering at all, especially the sum of the bromide and iodide. They show some values are positive here, some values are positive here. So other ions do not interfere at all. So these are sensitive for the anion. So this is another one. This is what is the looks like again the thiourea based receptor complex into the 1,3-disubstitute-calyx for arene the molecules, and these molecules, they also selective toward the chloride ion. And this is the how it looks like. All these compounds, they show the this anionic response, not cationic response. Anionic response. Cation shows the other way, and the anion shows this type of the behavior. And this type of behavior is being observed for the chloride ion, and this chloride ion, that is a different type of the membrane, and this is the data which we have is, and this shows the polymeric membrane also, and that shows this type of the data. And we also did the estimation of the chloride ion content in pharmaceutical and water samples. We find that volumetric methods that agree with the ion selective membrane which we have added, both methods they agree, and this is how the sensor can be successfully used to determine the endpoint potential titration of sodium chloride versus silver nitrate. You add silver nitrate solution, you will get this type of the curve. This is the first derivative curve which you can make is, and this you can determine the endpoint is. Now this is another one, nitrate anion selective sensor, and this nitrate anion selective sensor that has been prepared by using the 2 type of the complexes of the zinc and having the 2 type of the ligands. Ligands are your tetradentate ligands, chiral tetradentate ligands, L1 and L2. When we made the membrane looks like these 2 compounds. We incorporate 2 compounds. They are selective to the nitrate ion. And we also looked at the combination of the cationic complexes with dichlorobenzene, and also they show the behavior. The interference is not, it does not follow the Habermas theory. So because the deviation is there from Habermas theory based on the lipophilicity of these compounds, these anions. And we also prepared hydrogen ion selective electrode, hydrogen sulfate ion selective electrode based on the coumarin derivative. And this coumarin derivative was prepared in Korea in the Professor K's lab, and we incorporated that in the PVC membrane. We find that this is hydrogen sulfate. So what we did is we did some preliminary study. When we did some preliminary study, we did absorption spectra of this ligand, that is your coumarin derivative. When we did this, we find that nothing happens to this. Only hydrogen sulfate ion that is making some difference in the absorption spectra. And if you see here that when you have a fluorescence spectra, the quenching of this the quenching, because there is a this derivative which is which gives the fluorescence, and that fluorescence is being quenched in the presence of the other anion, but hydrogen sulfate anion that is not showing any quenching. So intensity is not being quenched, and that is why we carried out the titration of the coumarin upon adding the various amount of the tetrabutyl ammonium hydrogen sulfate in this material. And when we find this one, that with the hydrogen sulfate there is change of the absorption spectra. With the increase in the concentration of the hydrogen sulfate derivative, hydrogen sulfate compound, then the increase in the intensity. This helps us to measure the Jaws plot. When we carry out the Jaws plot, we find that this is giving you the 1:1 complexation take place. So 1:1 complexation is being measured, and then we incorporated the PVC membrane, and we find that this shows a very good response for the hydrogen sulfate. So hydrogen sulfate, and we did also the potentiometric selectivity of the hydrogen sulfate ion, and we find that all values are negative. So of these ions, which indicate there is no interference of the other cations. So and then we also did some measurements using the amino alcohol selective sensors. And in amino alcohol sensors, we have the different type of the again beta ketone derivatives, and we find that this is selective to particular type of the amino alcohol. Which amino alcohol? Which are having chiral center. So those amino alcohols were sensed by these ions. So we find that these amino alcohols S, and S, all these showing the response, others are not showing the response. So it means the chiral amino alcohols can be sensed by using this type of the materials. So we also prepared some urinal sensor. The urinal sensor was also prepared by using this type of the organochalcogen ethers based on azacalex for 3 arenes, and this provides the urinal sensor like this. So a response like this. Other ions are not showing any response. So we did also the selective data, and this is and the ion pair recognition work is not so far completed, and we are not able to solve this problem. The problem is that this is selective towards the chloride ion. This is selective towards the potassium ion. But when you have the mixture of these two means this compound. When you have this compound here, we expect chloride comes over here and potassium comes over here. So we expect this one. So this work is not still, we are not able to solve this problem. Since I am working in the field of surfactant chemistry also, so I asked one of my students, why not to make an ion sensor for the surfactant molecule, or maybe a cationic surfactant, or maybe an ionic surfactant. What we did is, we prepared an ion pair by using the 2 types of the surfactant. One surfactant was cationic, other was anionic. So what we did is, we prepared ion pair like this. So we prepared, for example, this is TTAB, and this is sodium sulfate, this forms the ion pair. This ion pair, which was recrystallized from the acetone, and then incorporated in the PVC membrane, this was selective to particular type of the cations. And this is how we prepared another one is also, and this is how we prepared another one also by using the ionic liquid. And when we prepared these sensors by using this type of membrane, this type of membrane, this type of membrane, and I take one of them, and if you see that this is forming a layer, and this provides where this potential becomes constant, this helps us to calculate the CMC. Critical micelle concentration can be determined by using this type of the compound. So we took the different compounds, triblock copolymer we added. In this way we were able to calculate some the analytical applications also. We did measurement of some of the compounds of the surfactant, and also we found that what type of the Colgate, what it contains, CPC, the cytipyridine chloride, TTAB, or benzyl chloride, the nasopil, which contains the BC as an benzyl conium chloride, and these proposed methods, they agree with the 2-phase titration method, they agree well. So this is the work which has been done by one of my students recently, and he prepared the rhodamine dimethylaminosulfide based electrochemical sensor for selective detection of the iron 2. What he did is that this is this looks like the yellow in color. This is a rhodamine dimethyl aminocinamide, and when we added iron to this, and if you see that the host one, this one, that gives you this peak, host pure RC, that the rhodamine derivative, that gives you this cyclobutamogram, and these are the two peaks corresponding to the oxidation of the two of the moieties of this compound. And when the oxidation takes place, this gives the peak. When we add iron to, there is a spectrolactum ring opening take place here, and iron 3 is being formed. And we find that also that this forms this complex formation take place. And in fact, with your naked eye also you can see that when you have this compound, this has a yellow color. When you add it as the iron, it forms the blue red color. And in fact, this compound is a complex, and this peak, this new peak, is formed by the addition of this reduction of this complex is take place, and this helps us to know this is how selectivity data is being calculated in DPP measurements. The peaks are the same with the addition of all these metals, but when you add iron 2, if you see this, the iron 2, when you add here, the iron 2, a new peak is being appeared over here because of the reduction of the RC iron 2 complexes take place. So the color change also take place. Then we did the potentiometric, the voltammetric titration. When we added titration, we added different amount of the iron pre, then so many equivalents. You change the equivalents, these peaks decreases in current, whereas the current increases over here. This helps us to know what is the concentration range. So this much is the concentration range, the peak current versus the iron 2 concentration, detecting limit 10 is -7. So we also did the potentiometric titration. How much time I have? So I will just finish up within 5 minutes, okay? So this is another one, and this is another one, iron 3. In iron 3 is also the similar type of the behavior, and if you look at this, this helps us to know the concentrations of the iron 3 can be determined very easily by this. DPP measurements also being carried out and provide to the sensing by the pH range, potentiometric titration. So this is again iron 3, and this is how the UV spectra, the fluorescence spectra, and selectivity towards the iron 3, and also the DPP measurements, binding constant can be calculated by voltammeter. Agrees well. This is the mechanism which we propose. So I think I have many other slides. This is for the copper sensing. This is for zinc. I should stop over here, I think. I know it's difficult to understand these things because they're such, pure such. This is the work of dopamine, nanoparticles with the efficient removal of anion surfactant. And then this is the students are working. I thanks all you. Okay. I know that this is very difficult to understand. My aim was only to
motivate young researchers who are in the colleges. They can take up this challenge to start with this type of the work, which is the cost is not very high. Just few chemicals are needed, a potentiometer which is needed is required, and they can start with this type of work. And this work always pays. So you modify the surfaces, you modify the electrode, you modify the selectivity also. This is how you can do, you can start researches with small amount of money. So with this, I thank you all for your kind patience, of course. And questions now?
Any questions?
Because it's a research, it's not general. So you can ask general questions, general chemistry, okay? Come on with PHB tree or something like that now. Electroanalytical techniques. Next time I will also make nanotechnology. So thank you very much.
Thank you, sir. Now I request Dr. Sunita Bansal to present the token of appreciation to sir.
Experimental session. Next experimental session.